Alrighty guys, we're going to go ahead and get started with our Square of Love notes, part 2. So these notes specifically are going to talk about combo circuits, sometimes referred to as complex circuits. And those circuits are just circuits in which we have some resistors that are in series and some resistors that are in parallel with each other. And we're going to try to figure out how can we solve for these types of circuits when we have both series and parallel and series all within one circuit. So let's talk about some rules first. First rule I want to talk about is the fact that we need to be able to identify what parts are in series or parallel. From that, we can simplify the circuit by combining those like parts. When we simplify this circuit, we need to redraw it with the simplified parts one at a time. And you'll see what I mean later on in the notes. Lastly, we're going to create a big square of love, all right? Because you can never have too much love. And we're going to do that once we have our circuit simplified down to just one part. So if we take a look at our circuit over here, we have a 120 volt power supply. We have our first resistor, and then over here, it breaks up into another resistor and then two more resistors over here. These resistors look like they're in series, but then these are on opposite sides. They each have their own path. So that might be parallel. That's where things get tricky. So let's start by looking at these two resistors here, R3 and R4. And the reason I'm going to start with R3 and R4 first is because you always start with series. If you have some combo or some complex circuit and you have something that looks like it's series and something that looks like it's parallel, you always need to start with the series. So I'm starting with R3 and R4. I identify that these are in series, meaning that they're sharing one path, and we can see that here. If I were to cut R3 off, the electricity could not flow through and R4 would not work. Vice versa, if I cut R4 off, the electricity cannot flow through and R3 cannot work. Now that I've identified those as series, I need to combine them. I remember that when combining resistors in series, I just need to add those together. But before we get to the math, I want to show you how we're going to write this new resistor. So when we combine R3 and R4, we're going to say that it gives us a new, air quote, resistor. And that resistor we're going to call is just R34. Notice that I just put these two numbers together. This isn't something that's super important, but it's the way that I like to do it because I think that it's a good way to differentiate between a series and a parallel when you are combining resistors. So now that we've combined them into our new resistor R3, R4, and we know that these are in series, we know that when resistors are in series, we just add them up. So R3, R4 is really equal to R3 plus R4. That means 30 plus 40, giving us a resistance of 70 ohms for our new resistor, R34. Now that we've simplified it, let's go ahead and redraw it. Over here, we've now combined it to be that R34, and we can see that R2 and R34 both have their own paths. Because they have their own paths, it means that these two are in parallel with each other. Now that we've identified them to be in parallel, we can go ahead and combine these together. When we combine resistors in parallel, and we're basically making a new resistor like we did before, we're going to write it as R2, so meaning one of these resistors, slash 34. This slash helps me understand that R2 and 34 are in parallel with each other. This slash just, again, shows that it's in parallel. Now that we've done that, we need to use our rule to figure out what the total resistance is of our new resistor. We remember that in parallel, the way we add up our resistors is using this equation, 1 over the total resistance. In this case, our total resistance would be R2 slash 34 is equal to 1 over R2 plus 1 over R34. If we do that, we get 1 over 20 plus 1 over 70. Find a common denominator, add them together, or just plug it into our calculator. So we get 9 over 140. Flip both sides. We end up with 140 over 9. If we simplify, that gives us 15.56 ohms. Remember, whenever we're finding the total resistance in parallel, this total resistance should always be smaller than any of the resistors that we are adding up. And the reason is, if we think about a parallel circuit, the more paths we add to that circuit, the less total resistance we're going to have. But we need to remember our circuit rules. For parallel circuits, we know that voltage is always staying the same because each of those resistors has their own path to the battery. And we know for series that current is staying the same because each of those resistors shares the same path to the battery. So that current, or the speed of those electrons, is stuck on that road. Imagine this is just a road on a street. It's a one-way road. All the cars are moving at the same speed. Now we can go ahead and write our given information. R1 is 10 ohms. R2 was 20 ohms. R3 was 30 ohms. R4 was 40 ohms. R3, 4, that was that new resistor we made by combining 3 and 4 in series. That was 70 ohms. And then R2/3, 4, that was that new resistor we made by taking R2 and combining it with R3, 4, but these were in parallel, gave us 15.56 ohms. So the total resistance here is in regards to the simplified circuit that we have. Okay, the total doesn't just mean adding everything up. The total in this case would just be, because this is a series circuit, 10 plus 15.56. That's going to give us a total resistance of 25.56 ohms. Next, the given information here is the power supply, and that's 120 volts. So our total voltage should be 120 volts. And now we just do what we've done before. We solve once we have 2 in a row, we solve for the last one. So we know the voltage, we know the resistance, we can solve for the current. Ohm's law tells us voltage equals current times resistance. So to solve for current, it's just 120 divided by 25.56. We do that and we get 4.7 amps. Now we need to refer to our current rules over here. We remember that in series, current stays the same. So if I look at my picture, I can see that the battery is in series with R1 and R2/3, 4. So that means that the current of 4.7 amps should be the same for R1 and the same for R2/3, 4. And that's what we get. Now that we have our currents, we can solve for our voltages. Voltage is equal to current times resistance. So 10 times 4.7 and 15.56 times 4.7. Do that and I get our voltages. 47 volts for R1, 73 volts for R2/3, 4. Now this is where things get interesting. We solve for all of this stuff, but now we need to start solving for our other resistors that are no longer in this picture. So that's why it helps to draw those pictures one at a time, because once you solve for the tiny one, now you start working your way back and solve for the other one. If we know the information for R2/3, 4, we remember that R2 is in parallel with 3, 4. What happens for parallel? Well, we know in parallel that voltage stays the same. So this 73 volts is what's going to R2 and what's going to R3, 4. And again, that's because those resistors were in parallel with each other. Now that we have that information, we can use our voltage and our resistance to solve for our current. So 73 divided by 20 and 73 divided by 70. We find out the currents, and the current is 3.65 amps for R2 and 1.04 amps for R3, 4. Now, if we think about R3, 4, R3, 4, if we take a look at our picture, was in series with each other. Because they were in series, they should have the same current, meaning that this 1.04 amps is the same here and the same here. Now that we know those currents, we can just multiply across to get our voltages. 30 times 1.04 and 40 times 1.04. And perfect, we completed our square of love. So really quick, before we end these notes, I just want you guys to quickly think about something. We know that for a series circuit, which is what we have here, our total voltage is V1 plus V2 plus V3, so on and so forth. In this circuit, though, our V1 is right here, and our V2 is right here. So if we do 47 plus 73, we actually end up with 120 volts. That works out perfectly. Now, if we take a look at R2/3, 4, we said that the voltage of R2 and the voltage of 3, 4 are the same. Perfect. But we know that current in a parallel circuit should add up to the total current. So 3.65 plus 1.04 equals that total current. In this case, the total current for R2/3, 4 comes from R2/3, 4. So 1.04 plus 3.65 should equal 4.7 amps. Slight rounding error, but we get that. Lastly, if we take a look at R34, the voltage is 73 volts. Since R34 are in series, that means that the voltage of one plus the voltage of the other should equal our final voltage. If we do that, we find out that 31.2 plus 41.6 is equal to, or roughly equal to, 73 volts. And all of that holds true. So I recommend after you guys have your square of love, that you go through and you just do that extra step just to make sure everything's all nice and neat and adds up to what it's supposed to.